Okay, so now we want to talk about finding the slope of parametric curves. So we first define our parametric curves, f of t and g of t. We need those to be continuous, right, on the interval where we're looking to do the slope of the curve at. And we need them to be differentiable. Then it turns out the slope of the curve at the point f of t, g of t, where again those values are somewhere in the interval ab, right, actually is just the derivative of the y function evaluated at t over the derivative of the x function evaluated at t, provided, of course, that the derivative of the x function is not zero. Right? If the derivative of the x function is zero, obviously we're leading to some undefined situation here. Okay, so that is the slope of the tangent line is just the derivative of the y function divided by the derivative of the f function evaluated at those points. Okay. So let's take a look at an example of this. Earlier we studied the parametric curve defined by x equals t squared plus 2, y equals 4t, as t ranged between minus 4 and 4. It was actually the one that we did the really long way, where we went and plotted a bunch of points to see what our curve is. Okay, and so we're now interested in particularly what is the slope of the curve when t is equal to negative 2. In other words, when we're on the graph at the point 6, negative 8, which is this point right here, we're looking to see what the slope is, looking to see what the slope of the curve is. So let's use our process, right? So we would take dy dx is equal to y prime, right? So in other words, I'll say it this way first, y prime of t over x prime of t. Y prime of t would just be 4. X prime would be 2t. And then we want to evaluate that when t is equal to negative 2. T is equal to negative 2. Okay, so we plug in negative 2, and here we would get 4 over negative 4. We'd actually get a slope of negative 1. We'd actually get a slope of negative 1. Okay, and we can see at least that lines up. We can see the curve at least definitely has a slope that's negative at that point. And here it's actually telling me that's a slope of negative 1. Slope of negative 1. Now, let's continue a little bit further with this, and let's graph the tangent line and the curve. So let's graph those together. I'm just going to do this on my Desmos app because it's much quicker to do it that way, especially since we've already graphed the curve previously. So here we are graphing x equals t squared plus 2, comma, 4t. Right, that's my parametric curve. And we need to range that from minus 4 to 4, but I'm going to put a constraint, call it A, and add a slider in, and I'm going to set my A to range from minus 4 to 4. And, you know, we're going to do a step of 2/10 on my slider there. So we can actually see the graph generating It's always nice to be able to do that, to see the graph actually generate, starting down at its low point. We can see it slowly coming up and then coming off to its high point. So let me just zoom in a little bit so we can see that. And there we are with our curve. Okay. And then the point we were dealing with was when t was equal to -2. If we go back and look that up from our table, t was equal to -2, x was 6, and y was -8. So at t equals -2, we're dealing with the point 6 and -8, and we know that the slope of the curve is -1. So using my point slope formula, y minus y0 equals m times x minus x0. Using that approach, we can put my curve in there as y minus 8, or minus a -8, be y plus 8 equals a -1 times x minus 6, and then just clean that up a little bit. So that'll be minus x and then a positive 6, but when we bring the 8 over, we would have minus x minus 2. That's going to be our line that passes through our point, 6, comma, -8, that's on the graph there. And then our line, we can see, is y equals, again, I just said it, but I'll say it again, minus x minus 2. Minus x minus 2. You can see it passes through the point. Now, there's one final thing I want to kind of point out here. This line is moving, the tangent line is moving with a slope of -1. And it's moving, tangent to the curve, just like it did before. The curve, though, as t grows, right, is actually coming up. The direction of the curve is actually moving up the other way, not moving left to right. It's coming back from the left, or from the right to the left right now. So if you were actually moving in the direction of the curve at this point, the way the curve is moving as the parameter changes, you actually have a positive slope of 1. So very important that this slope of the curve doesn't take orientation, it's just taking the slope of the xy curve. Right? It's not taking the direction of motion as t increases into account. It's just the slope of the curve itself. So that's an important distinction to make there, that when we find these slopes, it is not taking how t is changing into account. It's just talking about the physical slope of the xy curve, okay, without considering the orientation of the parametric curve. Okay, so it is just giving you literally the physical slope of the curve as it lies on the graph, as it lies in the plane, without taking direction of orientation and concern. That's an important idea here with this slope idea. And we definitely see that. That's part of the reason why I wanted to go through this example here and graph it, so that we could kind of make that point very clear, that it's the actual slope of the xy curve without considering direction from orientation. Okay, so that's what we're finding here when we use this approach, derivative of the y function over derivative of the x function.